Good morning, everyone. Welcome back to 1406. Um, just one announcement before we get started on today's lecture. Remember, on Thursday, you do have an exam. By the end of the day today, everybody should have already submitted their assignments that are going to have things to do with the next exam. And once everybody's submitted by the end of the day, I'll have those things, those assignments posted for you to study with. What we're going over today will not be on the exam. That's carboxylic acids, esters, amines, and amides. So you don't have to worry about that. That'll be on the fourth exam. Yeah, make sure you study for your test on Thursday. All right, so let's go ahead and get started. And let me move the view around here a little bit. There we go. All right, so today we're talking about carboxylic acids. And carboxylic acids are actually a lot like carbonyls, right? They're all part of the same group, like the ketones and the aldehydes. The only difference is that with a carboxylic acid, instead of having an H, like an aldehyde there on the carbonyl, or an R there, like the rest of the molecule, for a ketone, a carboxylic acid has a hydroxyl group. And we'll be talking a lot about carboxylic acids later on in the semester when we get into the metabolism section. But for now, that's what you need to know is carboxylic acids have as their substituent group off the carbonyl a hydroxyl group, right? So we can name carboxylic. We can name carboxylic acids very easily. All we have to do is take the E from the alkane name, and change it to oic, and you have the carboxylic acid's name. So, say you have methane, which means it has one carbon in it. That carbon is the carbonyl carbon. We call it the methanoic acid, right? Or for ethane, which has two carbons in it, here in the carboxylic acid version, the two carbons are the methyl group, and the carbon that's in the carbonyl carbon, that's ethanoic acid. Very simple, right? A couple extra examples here. We already know ethanoic acid, just went over that. Another common name for ethanoic acid is acetic acid. That's vinegar, of course. We have propanoic acid here, 3 carbon, carboxylic acid. And we have benzoic acid here, which is the one that has benzene in it, right? So benzene, take off the E, and then put in oic, and you get benzoic acid, right? And notice they all have hydroxyl groups. They all have hydroxyl groups. So, just to continue a little bit more on naming carboxylic acids, if you have extra constituents off the chain or off the benzene ring, you just name them like you normally name any other of the chains of carbons, right? The first carbon you start naming is the one that is closest to the end of the carboxylic acid. So if it's a straight chain, you start 1 on the carbonyl carbon, and then 2, 3, 4, right? So that's 4 carbons right there. And it's the third carbon that has a methyl group attached to it. So we call that 3-methyl butanoic acid, right? 3 because it's on the third carbon. Methyl because there's only a methyl there on that third carbon. Butanoic acid because it has 4 carbons, which is derivative from butane, right? It's a little different with the benzene ring on benzoic acid because you still start with the end that's closest to the carbon, carbonyl carbon, but in this case you're starting with the numbers, numbering the carbon on the ring. So when you do that, that means the first carbon that has the carboxylic acid attached to it is that one, carbon 1, 2, 3, 4, 5, 6, right? So there are 2 chlorines on there. There's 1 on carbon 2. There's also 1 on carbon 3. So that the name of this particular benzoic acid is because they're on the second and third carbons of the ring. Dichloro, because there's two chlorines and di means two. Benzoic acid for the rest of it, right? Pretty simple naming carboxylic acids. Here are a few more common for carboxylic acids you should know about. We have methanoic acid, also known as formic acid, this guy right here. Interestingly enough, one side of it is a carboxylic acid, and then the other side is actually an aldehyde. And if remember, if it was formaldehyde, right, it would have an aldehyde on both sides, if you recall. So we already talked about acetic acid or ethanoic acid, and then we have propionic acid or propionic acid, and then we just talked about butanoic acid, and butanoic acid's common name is actually butyric acid, right? So let's do some naming practice here. We'll start off with this one. We'll number the carbons. 1, 2, 3, 4, and 5. So it's 5 carbons. So you already know that's going to be a pentanoic acid, right, for 5 carbons. But there's also this methyl group hanging off right here from carbon 2, right? So that means it's going to be 2-methyl pentanoic acid. Naming carboxylic acids is that easy, alright? Next one, we have a benzoic acid here. We already know it's a benzoic acid because remember that this part is called the benzene, right? And here's the carboxylic acid. Put it together, you have a benzoic acid. You have a bromine coming off the ring right there, right? So you have to name it by the number carbon it is on the ring. So 1, 2, 3, 4, 5, 6. It's on the third carbon of the ring. So it's quite simply 3 bromo, right? Benzoic acid. Simple as that. Last one here. Luckily for us, is a straight chain, so we'll start naming numbering from there. 1, 2, 3. There's a methyl group right there on the second carbon. So that's quite simply 2-methyl. Right? And then there are 3 carbons there. So it's propanoic acid. Easy as pie, easy as pie. So there's some common carboxylic acids, of course, that we were just talking about, but formic acid, which we mentioned, is actually the acid that is in a red ant sting, which happens a lot in Texas. I remember when I was living in Alabama going to grad school out there at Auburn, and we had ants out there too, but they were really just sugar ants, right? So they didn't really bite you. And come back here to Texas, and holy crap, the the red ants, those fire ants, they're pretty bad here in Texas. I believe their scientific name is Solenopsis invicta, and the acid that's in their sting is formic acid, and that's why it irritates your skin so much. And then everybody knows that ethanoic acid or acetic acid is basically vinegar. It's not basically vinegar; it is vinegar. Yep. So let's talk about some polarity and properties of carboxylic acids, right? The carboxylic acids are strongly polar because they have 2 polar groups, right? You have the hydroxyl group right there, which is very polar because it's partially positive right here on the hydrogen side, partially negative on the oxygen side. And we already know how polar the carbonyl group is, right? Positive over here at the carbon end, and then at the end of the carbonyl where the oxygen end is very negative. So that makes it a very polar molecule, very polar constituent, polar constituents. And this part right here, though, is a very interesting fact, is on the wrong slide. So we'll get back to that later. So when we're talking about polarity, if something's superpolar, what does it usually mean? If it's superpolar, it is soluble in water, right? So let's take a look at some of these right here. They're very soluble in water because they can form hydrogen bonds. The oxygens of the carbonyls can form hydrogen bonds because they're negative and they're partially negative, and they can form hydrogen bonds with the partially positive hydrogens of the water. And then on the carboxylic acid side, the oxygen, of course, of the carboxylic acid is the negative end, right? It can form hydrogen bonding with the partially positive hydrogen atoms of the water, just like the carbonyl carbon can, but it has the added added hydrogen on the hydroxyl group that's partially positive that can also hydrogen bond with the oxygen of the water, right here, which makes it super soluble. In fact, carboxylic acids have the same trend in solubility in water as other hydrocarbons do, right? As more and more carbons get added, the more nonpolar character gets added to the molecule. And the bigger the chain, or the more carbons there are added, the less soluble it gets, right? It's the same kind of trend. So as the number of carbons increase, the solubility of the carboxylic in water is reduced, right? Make sense? Yep. We all know, though, that, for example, ethanoic acid or acetic acid is super soluble in water, right? Super soluble. So, we talked about this previously when we were talking about acids and bases and how acetic acid was actually a very weak acid. Why is it a weak acid? Well, it's a carboxylic acid, and carboxylic acids are weak. They ionize very weakly to produce carboxylate ions and hydronium ions in water, just like you see here. We have acetic acid, add it with water, and we get the acetate ion and the hydronium ion, right? Excuse me. So pretty simple there, because we've already talked about acetic acid in the past. Oh, and just so you know, we haven't really talked about this much, but one of the reasons why acetic acid is soluble in water and also is acidic, weakly acidic in water, is because it can easily lose this proton right here, right? And the reason why it can lose this proton is because once it loses this proton, the oxygen becomes negative, right? And the acetate ion. And there's this thing that we call resonance in organic chemistry, where a negative charge, which is also known as an electron, can move throughout bonds like that, right? And when it does that, it actually forms a double bond right there between the carbon and the oxygen. And when that happens, the single bond, one of the bonds from the double bond of the carbonyl carbon, in the form of an electron, will go up here to the oxygen, right? Why does it do that? Well, it does that because, remember, carbon can only have 4 bonds, right? And then you end up with another structure that looks like this. Right? And then the same thing can happen again, where the electron from that extra oxygen, that extra electron on that oxygen comes down, reforms a double bond, right? And then moves that bond over back to this oxygen, right? And you get back to this original structure that we had before. And that's actually called resonance. We talked about that before with benzene rings. Because in benzene rings you have double bonds, like that, and each bond can move around the ring like this in resonance, right? And when it does that, it stabilizes the molecule. And stability is what molecules like, right? Every molecule wants to be stable. And it turns out that when acetic acid or ethanoic acid loses that hydrogen right there to the water to make the hydronium ion, it becomes a very stable acetate ion because of the movement of the electrons between the carbonyl carbon and the two oxygens that it's attached to, right? So let's talk about those acetate ions, also known as carboxylic acid salts, right? They're produced, like I said before, when you get the neutralization of carboxylic acids with a strong base. This time, instead of using water as our base, we're using sodium hydroxide or potassium hydroxide. When you do that with methanoic acid, add in sodium hydroxide, what do you get? You get sodium methionate, which is an ionic compound, right? That has the acetate ion right there. Oh, sorry, the formate ion right there, right? And the sodium ion there. And the hydrogen that used to be here, right? It's no longer here because it was added over to the water, right? Added over to make the water from the hydroxide ion of the sodium hydroxide, right? Same thing happens to benzoic acid. The hydrogen from the benzoic acid comes over here, joins up with the OH, hydroxide of KOH, potassium hydroxide. It makes water, leaving behind a negative charge on the benzoic acid, so that's the benzoate ion, with the potassium ion, both ionic compounds now, right? We have a couple more examples of that down here. Sodium benzoate, one that everybody should know really well, is monosodium glutamate. That's a preservative, a meat tenderizer. People used to be really afraid of eating monosodium glutamate because they thought that it was some kind of poison or something like that. But it turns out that MSG, or monosodium glutamate, is just an amino acid, which our bodies don't make naturally, but we need them to survive. They're an integral part of our proteins. All right. So, how do you name carboxylate ions? All you do is change the ic to ate. It's just like any other acid ion, right? Any other conjugate base of an acid. Like I already said, ionic compounds with strong get formed with strong attractive forces. These guys are all solid at room temperature. They have very high melting points, and they're usually soluble in water. Why? Because these ionic compounds, they are ionic, right? And they are very soluble in water because they're ionic, because water is polar, and they are polar by definition because they're ionic. Oh, and here's the part that was on the previous slide on accident, but it's supposed to actually be here. Carboxylic acid salts are used as preservatives and flavor enhancers. So things like sodium propionate, that's used in cheese and breads. Sodium benzoate inhibits the growth of mold and bacteria and is added to fruit juices, margarines, relish, salads, and jams. Monosodium glutamate, which is MSG, it's added to meats, right? Like fish, vegetables, baked goods, to enhance the flavor, right? So it turns out that carboxylic acids are actually very important to us in our metabolism as well. And we'll go through a lot of this in much more detail later on in the semester when we actually go through the metabolic pathways like glycolysis and citric acid cycle and electron transport chain and things like that. But I just wanted to point out parts of the chain and parts of the pathways that actually contain carboxylic acids now, right? So first, let's talk about glycolysis, right? Generally, glycolysis, glucose is broken down into pyruvate before it goes into the citric acid cycle at the step of pyruvate dehydrogenase, right? So pyruvate dehydrogenase will actually turn pyruvate into acetyl-CoA, and then acetyl-CoA goes into the citric acid cycle, and then in the citric acid cycle, we'll start getting energy payoff, right? But during times of strenuous exercise and oxygen levels are low, which is also known as anaerobic conditions, instead of going into pyruvate dehydrogenase and becoming acetyl-CoA, pyruvic acid or pyruvate is reduced to give lactic acid or the lactate ion, right? So here's pyruvic acid. You notice here is the carboxylate part of pyruvic acid. It gets reduced by two hydrogens, right? With two hydrogens there, and you get lactic acid. And that's why your muscles kind of burn after you've been working out a lot, right? We'll go through that in much more detail later on in the semester, anaerobic respiration. So let's jump into the citric acid cycle real quick here. So in the citric acid cycle, we have dicarboxylic acids and tricarboxylic acids that get oxidized. Those are citric acid here and alpha ketogluteric acid, which I actually just call them citrate and alpha ketoglutarate, right? And so, because when they're in the citric acid cycle, they're actually the ion form, right? The ion form. So when they're oxidized, they get decarboxylated, and that means that they actually lose a CO2 in the process. So that CO2 is important. Why is that CO2 important? It's because that's the CO2 that you breathe out, right? When you exhale CO2, that's where that CO2 is coming from. It's coming through the decarboxylation of those tricarboxylic acids, those di and tricarboxylic acids, right? And those will go further into becoming part of the electron transport chain after the citric acid cycle, right? So, but at the start of the citric acid cycle, citric acid is oxidized to a 5-carbon glutaric acid, right? So here it is right here, citric acid, and it's getting oxidized to, or citrate is getting oxidized to alpha ketoglutarate, right? And it looks like there's only one step here, but in fact there's many steps between here and here. Many enzymes have to take their chance at working on citrate before it actually becomes alpha ketoglutarate, and then you get this. You'll get CO2, right? So multiple steps in between. So one of them is citrate actually becomes a connotate first, right? Which you don't really need to know that, but I just wanted to mention that. And then after that, a connotate becomes, I'll just label that with an A because you don't really need to know that. After connotate, it becomes isocitrate. And then after isocitrate, it becomes alpha glutaric acid or alpha ketoglutarate, right? So there are many steps in between, but the point is we have 3 carboxylic acids here, right? And we have 2 carboxylic acids here, right? And when it gets oxidized, you release the CO2, which is the CO2 that you breathe out, right? So the citric acid cycle continues. Excuse me. As alpha ketoglutarate loses a second CO2 to give the 4-carbon succinic acid, right? And then so we still have 2 carboxylic acids there. And then fumaric acid or fumarate still has, after it gets oxidized, still has 2 carboxylic acids there. And then at malic acid, still 2 carboxylic acids there, right? And then after that, we have oxaloacetic acid with 2 carboxylic acids there. And if you didn't already know, oxaloacetic acid is the last step of the citric acid cycle. After that, it becomes citrate again. It is called a cycle, right? Oh, sorry, my head is blocking that. Let me go back over here. Citrate, which is the beginning of the citric acid cycle, right? And it is a cycle, that's why it becomes citrate at the end again. And it goes through the cycle again, over and over and over again, right? But the point of this slide is to demonstrate to you how the citric acid cycle has multiple carboxylic acids that are involved. So enough about carboxylic acids. We'll talk a lot more about them when we start talking about glycolysis, the citric acid cycle, and the rest of the metabolic pathways. Next, let's talk about the esters. What are esters? Well, they were discovered by chemists in the 1800s, right? From the salicin. Wow. Salicin. From the willow tree bark, right? And these leaves were actually responsible for pain relief, right? Turns out that salicin can be converted into salicylic acid in the body. That actually irritates the stomach lining, but salicylic acid can be changed into acetylsalicylic acid, right? Bayer found that out, which is less irritating, but it also is effective pain relief. And by the way, if you didn't know, acetylsalicylic acid is actually aspirin. Right? It's actually aspirin. So, we were just talking about carboxylic acids, and we have acetic acid here, right? What is it actually an ester? An ester is when the H here of the carboxylic acid actually becomes something else. An R, right? A rest of the molecule. In this case, for methyl ethanoate or methyl acetate, this R is a methyl group, right? So those are synthesized from the reaction of a carboxylic acid and an alcohol, right? They're found in fats and oils, and they're responsible for all the aroma and flavors of bananas, oranges, and strawberries, right? Those are esters. So everything you smell that's fruity is basically from an ester. All right. The reaction of a carboxylic acid and an alcohol in the presence of an acid catalyst and heat produces an ester, right? So basically what you're doing is you're replacing the hydrogen of the atom, like I was saying in the previous slide, right? In the carboxylic acid's OH group with the alkyl group that's from the alcohol, right? I already demonstrated this a little bit on the previous slide, but let's review it and look at it one more time, right? We have acetic acid here, right? We're going to treat it with some methanol, some acid here, that's what the H plus is, right? Protons, some heat, and what happens? This part right here, the OCH3 moves over here, right? And takes the place of that H. Of that OH rather, I'm sorry, of that OH. And then the OH combines with the H that was on the methanol. And what do you have left? You have water and methyl acetate. Right? Quite simply, you are replacing the OH, the hydroxyl group, of the carboxylic acid with the alkyl group, minus the proton from the OH, of the alkyl group. Right? So here's another example here. We have again acetic acid. This time we have propyl alcohol or 1-propanol. And then when we treat it with some acid and some heat, what do we get? Well, the first thing you should know getting, right? Always remember, those right there combine with each other to make a water, right? And then the rest of it combines with each other to make propyl acetate or propyl ethanoate. And that is called an esterification reaction, or the synthesizing of esters. So let's name some esters now. Pretty simple to name an ester. The first word of the ester's name is the alkyl part from the alcohol. And the second word in an ester's name is the carboxylic acid's name. Sorry, carboxylate's name from the carboxylic acid, right? So let's take a look at here at this one. We have the carboxylate here, right? There's 2 carbons there, so that was ethanoic or acetic acid, right? And then we have the ester part here from the alcohol. It was methanol. So we added together the ethanoic and the methanol. And what do we get? We get methyl ethanoate. Right? The methyl part right here comes from that methyl group. And then the ethanoate comes from that, the ethanoic acid. Or we could do the common name, which is acetic acid combined with methyl alcohol, and we get methyl acetate. Right? Some examples here. Here is ethyl ethanoate, right? 2 carbons there for the ethyl group, right? And then the acetate group there, or the ethanoate group there. Methyl propionate, the methyl group right there, right? And then the propanoate group there, 3 carbons, right? So that's methyl propanoate. And this one's easy because we have an ethyl group there, and then the actual carboxylic acid side is a benzoate, because that's a benzene right there, right? So we get ethyl benzoate. Let's practice this a little. We have here how many carbons? 1, 2, 3. That means that's going to be a propyl, right? And then we have this part here, which looks like an acetic acid or an ethanoic acid, the same thing, right? So that will be propyl, either ethanoate right? Or it could be propyl acetate. I will accept either answer, right? Either answer is correct. Let's do this one now. We'll have 1, 2 there for the, 1, 2, 3 there for the carboxylic acid part. And then for the alkyl part, we have 2 there, so that's ethyl. So the name of this guy is ethyl, right? Propanoate. Pretty simple naming esters. After you get past all the alkyl groups, alkanes, alkenes, alkynes, and all those, naming gets super easy, alright? Alright, so a little more about salicylic acid, right? So Bayer, back in 1899, Bayer actually produced the ester of salicylic acid and acetic acid, right? And that was the acetylsalicylic acid. That's always been very difficult for me to say. Acetylsalicylic acid, right? And I already told you before that was aspirin, right? So here's the reaction. We have our salicylic acid. I always say cyclic for some reason, but it's not cyclic, it's sialic. So we have our carboxylic acid, which is the salicylic acid. All right. And we have our acetic acid with some heat and some protons. All right. Acid. We get acetylsalicylic acid, right? And you can see there that this went there, and then this, the OH here, took off that proton, making you the water, right? This is actually an experiment you would have been able to do in lab, which is actually kind of fun, but you would have been able to do that in lab had we not been restricted to online classes only this semester, because that's actually an experiment we do. I did it when I was in organic lab, and I tried to actually take some of it, and I didn't die from it. It did help me with my headache, but I thought it was a huge accomplishment that I was able to take or try some of the the aspirin that I had synthesized myself in organic lab. I was really dumb back when I was in undergrad. I was very dumb. So anyway, if you didn't already know, a lot of people take low dose aspirin to lower their risk of heart attack and stroke because it thins the blood. Right, it thins the blood. Another one that salicylic acid does is that you can actually combine it with methyl alcohol, and you can make methyl salicylate, which is wintergreen, right? It's got a minty flavor and odor, right? And it's used for skin ointments. It acts as a counter irritant. It produces heat to soothe sore muscles. So, and everybody, I don't know if you actually get to make that wintergreen in lab here, but when I was in undergrad at Sam Houston State University, I'm pretty sure we made wintergreen as well. Or maybe we did that with bacteria. Oh, that's what we did. In biochemistry lab, we actually synthesized DNA that would be transformed into E. coli cells. And if you fed them salicylic acid, they would make wintergreen. So you would open up the petri dish and smell the bacteria. It wouldn't smell like, butt like bacteria smells like, but it smelled like wintergreen. So that was really fun. And there was another one where we made one that smelled like bananas too, I think. It's too bad we don't get to work in lab this semester. I missed that. Oh, speaking of smelling like bananas, there are esters in fruits and flavorings, right? So propyl acetate or propyl ethanoate is the smell you smell in pears. Pentyl ethanoate or pentyl acetate is the smell you smell in bananas. Yes, we did that yes, we definitely did that well, I wonder why my camera was like having trouble focusing just now. It's still having trouble focusing. I'm sorry about that. Anyway, octyl ethanoate right there, or octyl acetate, is in oranges. That's what you smell when you smell oranges. And then ethyl butanoate is the smell from pineapples, and pentyl butanoate is a smell from apricots. Apricot. Is it apricots or apricots? Oh well. More naming practice. Time for more naming practice. Let's see here. Okay, so this is pretty simple, right? We have we have a butanoic acid, right? Because there are 4 carbons. 1, 2, 3, 4. So that's a butanoic acid. And then on the 3rd carbon, there's a bromine. So what is its name? 3-bromo butanoic acid. All right. All right. Let's look at this guy now. Oh, wow, we have an ester here, not a carboxylic acid. All right, so we have the propanoate right there, which is the carboxylic acid part of the ester, right? And then we have, on the other side of the ester, we have the ethyl. So that would be ethyl propanoate. That simple. That simple. You didn't even have to number the carbons because there were no substituent groups hanging off the side of the chain. All right, so let's talk about breaking down some esters, right? Also known as hydrolysis. If I haven't already said this before, but I think I have said it before, hydrolysis basically means cutting bonds with water, hydrolysis, right? So we're using water to cut the bonds of the esters, let's break them in half, right? So we can do that 2 ways, either with acid hydrolysis or base hydrolysis. And in acid hydrolysis, we'll look at this example here. We have methyl ethanoate or methyl acetate. We add water to it right here with some acid and some heat, protons and some heat, right? And what do we get? We get the carboxylic acid and the alkyl group that made them, right? So, not the alkyl group, sorry, the alcohol that made the ester, right? So the carboxylic acid that made the ester is there, which was ethanoic acid, right? Or acetic acid, right? and then the alcohol that made it was methanol, right? Because the methanol part right there, it went back with the H from that water. Remember, this water was used to make this methyl acetate at the beginning, but now we're breaking it apart. So the OHCH3 of the methanol goes back to the hydrogen of the water, and the OH from the water goes back to being with its carboxylic acid. Sorry, that was a little confusing there. The way I drew that. Let me clear that, and we'll do that one more time. So the yes, the OHCH3 of the methanoate, right, recombines with the H from the water that we used to the H from the water, and then the OH that was from the carboxylic acid that we used to make the methyl-ethanoate goes back to combine with the carboxylic acid, the carbonyl, and that's why we get ethanoic acid or acetic acid with methanol, right? With methanol. So we can do the same thing with base hydrolysis too. This is also known as saponification because this is how they make soap. And in this case, we have here the methyl-ethanoate again, or methyl acetate, the same example as above, where this part is the carbonyl part and this part is the alcohol part. We add that to the base, right, with some heat, and the carbonyl part, or the acetate part, right there, combines with the sodium to make sodium ethanoate, the ionic compound that is super soluble in water, and then that leftover OH the H of the leftover hydroxide combines with the methanol part, and it becomes methanol, which is also actually very soluble in water. Interesting, right? And this is how we make soap, by the way. All right, so let's discuss amines now, right? So amines are derivatives of ammonia, NH3, which looks like this, if you recall. NH3, right? Remember, we also had the ammonium ion too, which looks like this. It had 4 hydrogens, and since it had an extra hydrogen, which is also a proton, the nitrogen gets a plus sign, right? Well, what are amines? They are actually derivatives of those ammonia, right, that have aromatics or alkyl groups attached to them, right? So here we have an amine where there's an ethyl and a methyl group attached, right, to the original nitrogen. And here we have an amine where a benzene is attached, right? So amines are actually classified, just like alcohols, as either primary, secondary, or tertiary. And I'm sorry, I drew all over these pictures right here, so let me clear it real quick. There we go. So we have, let's start out with ammonia, right, which I just drew a second ago, a nitrogen with 3 hydrogens. Then we have methylamine, right, and methylamine is a primary amine. Why? Because there's only a single methyl group attached to the nitrogen, or replaced, right? A single hydrogen has been replaced, so that makes it a primary. A secondary amine has 2 of the hydrogens replaced. In this case, it's 2 methyl groups, so we'll call that dimethylamine, right? And that's a secondary amine. And in a tertiary amine, all 3 hydrogens are replaced, right? And so we call that triethylamine. So how do we name amines? How do we name amines? Well, they're named just by simply their alkyl name and the word amine, right? So in the case of this one, that's an ethyl group with an amine, so it's ethylamine. Here, there are two methyls connected to the amine, so that's dimethylamine. And here, we have a methyl and a methyl, so that's two methyls and an ethyl. We'll do this alphabetically, right? So it's ethyl dimethylamine. That simple, right? How do we name aromatic amines? Well, this is a common compound, aniline, right? And aniline has the amine group connected to the benzene right there. Which, by the way, this is a what? This is a primary amine, right? So when we look at this one, there's a bromine connected to the fourth carbon from the amine, right? Carbon 1 is there, 2, 3, 4. So quite simply, it is 4-bromoaniline, right? So this one is a little different. The next one's a little different. We have our amine here, right, connected to one hydrogen, but then to one benzene. But then here, what is that? That, when there's nothing there, there's a methyl group there, right? CH3. So this automatically is what? A secondary amine, because two of the nitrogens have been replaced by something. And since we already know that it's part aniline, right, we could go ahead and say it's an aniline. And to denote that there's a methyl group connected to the nitrogen, that's why we put an N there. So it's N-methylaniline. So that's the only time it gets a little bit different, when there's a substituent group connected to the nitrogen of an amine, right? That's a little bit different. Let's keep on going with this. Oh, I'm sorry. Back. Just so you're familiar with the line angle drawings, right? We have here propylamine, which is a primary amine, right? One carbon there, two carbons there, three carbons there. So it's a propyl, and then amine attached to it, right? Again, ethyl propylamine there because there's an ethyl group there, and there's a propyl group there, and it's a secondary amine. And then diethyl methylamine because there's two ethyl groups for diethyl and one methyl there, diethyl methylamine, which is a tertiary, right? It's a tertiary. So let's talk about some of the solubilities here of amines. Primary and secondary amines with fewer than 6 carbons are soluble in water. Right? I didn't mean to write all over that. Let me just clear that and write that again. Primary and secondary amines, right? Amines that have 1 or 2 hydrogens replaced with fewer than 6 carbons are soluble in water. And it's just like all the other rules when it comes to solubility in hydrocarbons, right? The more hydrocarbons there are, the more nonpolar it gets, and the more nonpolar it gets, the more likely it won't be as soluble, right? Thus, they can form hydrogen bonding with water molecules. Tertiary amines, on the other hand, can form hydrogen bonds only with water molecules. So, what's the difference there? I had to read it a second time myself because I'm the one that typed this. Anyway, they can form hydrogen bonds with water molecules, but also other things too that are electronegative, right? But tertiary amines can only form hydrogen bonds with only water molecules, right? So because amines contain a polar NH bond, right, they can form hydrogen bonds in water. So primary amines can form them with water, right? Secondaries can form primary amines can form more hydrogen bonds than secondary amines can, right? But tertiary amines have no hydrogen on the nitrogen atom and can only form hydrogen bonds with water from the nitrogen atom. And that's the reason why, right? That's the reason why a tertiary amine can only form with water, because the only thing it has to form with is its nitrogen, right? You have to have, when you're doing hydrogen bonding, nitrogen, hydrogen, like that, right? And then hydrogen bond with water, right? And you could also go the other way. Like that. So that's what tertiary amines cannot do. Primary and secondary amines can do it, right? Because they have at least one hydrogen there to form a hydrogen bond both ways with water or any other hydrogen bonding capable molecule. But tertiary amines don't have any hydrogens. They're just N R all the way around, right? N with R, rest of the molecule all the way around with no hydrogens there. So the only thing that can hydrogen bond is quite possibly the nitrogen, right? And that can only bond to the hydrogen of water and nothing else. That's what that means. Sorry, I typed that and I forgot what I meant by that. But that's what I meant by that. So like alcohols, the smaller amines, including tertiary ones, are soluble in water because they form hydrogen bonds with water. But amines with more than 6 carbon atoms have the effect the hydrogen bonding in which it is diminished, right? It diminishes the hydrogen bonding, so it's less polar, right? So, and then also I said this before too, nonpolar hydrocarbons chains can decrease its solubility in water. So it's basically that line. I'm repeating myself. Sorry. Repeated myself a lot on that. Well, probably because it's super important. You should remember it. And then I have some examples next here. So, but I need to put those up and clear. There we go. All right. So, what is this guy here? This is a propylamine. Right, and it is a primary, which means it's soluble in water. Right. Here's a secondary. The secondary is ethylamine. Sorry, methylamine. I forgot the methyl behind it at the other end. Ethylmethylamine. Right? That's a secondary amine. Still can form a lot of hydrogen bonding there because it has an H, so it's soluble. And then we have, that's weird, that's butane. That's not even an amine. Man, this slide's full of surprises is what this is. Oh, sorry, and also my head is blocking it. This is actually butane. Any guesses on whether it's soluble in water? It's not. Not soluble in water. This slide is full of all kinds of surprises, right? Not an amine, not soluble in water, do not pass go, right? Not tertiary, not secondary, not primary, not even an amine. All right, next. Let's just keep going. Next. Neutralization actually forms amine salts, right? And the interesting thing about that here is that it's actually amines in fish react to the acid in lemon juice, right? And so that actually neutralizes the fishy odor in fish when you eat. I always wondered why we have lemon with fish, which I don't really like eating fish, but I've always wondered about that. But it's because it wants to remove. They use it to remove the fishy odor, right? The fishy odor, right? So let's neutralize an amine, right? We have methylamine here. We're going to add some hydrochloric acid in there, right? And what we get out of that is methyl ammonium chloride, right? Which is the salt amine. So when we did this with hydrochloric acid, we did this because amines actually act as a base, Bronsted-Lowry bases, right? And so they'll accept protons, right? And when you add hydrochloric acid to methylamine, the amine takes that proton from the hydrogen right there, leaving you with methylammonium and the chloride ion. Same thing happens here. These electrons from this amine will take that proton from the chlorine, giving the dimethylamine a positive charge, making it the dimethylammonium ion, side by side with the chloride ion, right? And those are the amine salts. Let's talk about the ammonium salts real quick. Excuse me, my nose is very congested today. Yeah, good morning. Anyway, ammonium salts. So ammonium salts are usually converted to their, amines are usually converted to their ammonium salts before being used as drugs. So funny, because the drug we're talking about right now is ephedrine, or also known as Sudafed, or Sudafed, right? But I also actually call it Sudafed, is the actual spelling of it, right? And what does it do? It actually helps with congestion, right? It's a decongestant. This is the stuff that you actually get from the pharmacist. You don't need to have a prescription for it, but you just ask them for it, and they check your driver's license to see if you have bought any in the past, because you can actually take the ephedrine hydrochloride here, or Sudafed, and turn it into crystal meth. It's actually very easy to do that. And so people used to buy a crap ton of Sudafed and convert it to crystal meth and then sell it on the street. So now that's why when you want real Sudafed, you have to actually go to the pharmacist and have them check your driver's license to see if you've bought any in the past couple of months. And I believe you're allowed to buy 30 pills. Don't hold me to this, but I think you're allowed to buy 30 pills of 120 milligrams each every 2 weeks to a month. And any more than that, they won't let you buy any Sudafed, which I need some today because I'm super congested right now. But yeah, that's the real Sudafed. There's also this other stuff called Sudafed PE, which is Sudafed phenylephrine. It doesn't do anything for you at all. If you are congested, get yourself some Sudafed, right? Real Sudafed from the pharmacist. You have to actually go to the counter and ask them for it. Another one, diphenylhydramine, right? That's found in Benadryl. It's used for allergies, right? Used for allergies. One of the reasons too why drug companies use the ammonium salt version of a drug in like a pill or something like the Sudafed, for example, is because they're more soluble in water, which means that your body can absorb it easier, right? If it was a polar molecule, and if it was a non-polar molecule and you tried to take it as a drug, it wouldn't do so well because your body wouldn't be able to actually absorb it. It has to be soluble in water. Let's talk about more drugs. So another ammonium salt that's pretty famous, cocaine. So my girlfriend, she's a forensic scientist too, and she works in drug chemistry, and she's always dealing with cocaine, right? And I used to not know the difference between cocaine and crack cocaine. And it turns out that the difference between cocaine and crack cocaine is this. Cocaine hydrochloride, right, is this right here, where it has the salt version, right, of the cocaine molecule. The ammonium salt version of the cocaine molecule. Because there's a positive charge right there, and there's a negative charge right there from the chloride, and that makes it ionic, so it's a salt version. So the free-base cocaine, or also known as crack cocaine, right, which is actually not as good, because it doesn't absorb into your body as well, and I'm just speaking as a chemist, right, And why doesn't it absorb into your body as well? It's because this is a nonpolar compound, right? Like generally nonpolar, because let me rephrase that. Less polar than this over here, right? Because there's no ionic charge there, right? There's no polarity in the plus and the minus, right? Like it had over here, like it had over there, right? So that's crack cocaine, the free base cocaine, right? So if you wanted to turn cocaine hydrochloride to crack cocaine, all you would have to do is treat it with some sodium hydroxide, and what you get left over is this hydroxide here, right? Taking off this proton. After it takes off the proton, you lose the plus charge on the nitrogen, and then the proton goes over to the hydroxide, making the water from the sodium hydroxide, and then the chlorine combines with the salt from the sodium hydroxide, and so then you're left with the crack cocaine plus salt plus water. But yes, that's the difference. Interesting stuff. I learned a lot of stuff about drugs from my girlfriend because she works in drug chemistry as a forensic scientist. Oh, here we go. Here's something that's helpful to people actually. Alkaloids, right? So, alkaloids are physiologically active compounds produced by plants that contain nitrogen, right? And they're used as anesthetics, antidepressants, and as stimulants, but they are habit forming, right? So one of those alkaloids is nicotine, right, from cigarettes. What does this do? It increases the level of adrenaline in the blood, increases the heart rate and blood pressure. Maybe nicotine's not that good for you, right? There's also caffeine. Holy crap, I probably drink like a gallon of iced tea every day. I started gaining a lot of weight, so I cut out the sugar. So it's not sugar iced tea, like it's no sweet tea, which is it's blasphemous here in the South, drinking non-sugary tea, unsweet tea. But it's definitely a lot healthier. But I still have to have my tea, so I'm always drinking unsweet tea, like in my tumbler here. It's all unsweet tea. I drink like 3 or 4 of those a day. Anyway, so caffeine is an alkaloid, right? Found in coffee beans, tea, soft drinks. It's also a stimulant of the nervous system, and it increases alertness, but it can't cause insomnia. I will say it's never caused me insomnia. Some other helpful things: morphine and codeine. They're also alkaloids that are from the Oriental poppy plant, and they can be used as painkillers, right? And here's the structure for morphine, and it's tertiary amine there, and then here's codeine there with its tertiary amine there. All right. Caffeine also has a tertiary amine there. All these are tertiary amines, right? Except for no, that's also a tertiary amine. They're all tertiary amines. All right. Oh, we're getting close to the end of this lecture. This is longer than I expected it to be, but it'll be the only one for this week, all right? Because you have a test on Thursday. Remember to study for it. Last but not least, let's talk about amides. Amides are very similar to amines, right? But what they are is that they are derivatives of carboxylic acids in which the nitrogen group, right, or the amine group, replaces the hydroxyl group on carboxylic acids, right? How do we do it? Well, if we want to just take a cursory look at it here, we have a carboxylic acid with an OH there, and it gets turned into NH, and that makes it an amide. So the new name now is ethanamide, right? Or acetamide. And we know the carboxylic acid form, it's everything we already know, which is acetic acid. So this happens through a process called amidation. That's how we make amides from carboxylic acids. Excuse me, my nose is stuffy. So here's the carboxylic acid part right here, the propanoic acid part. With being treated with heat and ammonia, the hydroxyl part will combine with one of the protons from the ammonia, right? And make water, leaving behind the NH2 or the amide part to recombine to make propanamide, right? Or propiamide. Cool. This can happen with a primary amine as well, right? Same thing again. We have propanoic acid here. The OH from the propanoic acid would combine with the water. I mean, with the one of the hydrogens from the methylamine, making water, and then that makes it so that the amide part, which is the NH2, sorry, NHCH3 right here, can combine with the propanoic acid to make N-methyl propanide, N-methylpropanamide, N-methylpropanamide. Ah, wow, that's hard to say. N-methylpropanamide, amide, propanamide, N-methylpropamide. That's good enough. We're not here to do pronunciation tests, right? Yeah. All right, so let's name some amides now. How do we name them? In both the common and the IUPAC names, amides are named by dropping the oic acid from the carboxylic acid, right? Or the ic acid in the common name, right? From the carboxylic acid, and adding the suffix amide. Wow, that's simple. Simple, right? And then, if they're alkyl groups attached to the nitrogen of an amide, they're named with the prefix N, followed by the alkyl name, which we saw before with the amines, like the N-bromo benzoic benzamide. Was that what it was? I can't remember what the example was before. You can go back and look. Anyway, so here we go. We have butanoic acid or butyric acid right here, right? So that gives us the last part of the name, right? And then we have here the dimethylamine part, and both methyls are connected to the single nitrogen there, right? So that's why it's called NN. That tells you there's two methyls that are connected to the nitrogen, NN dimethylamine, right? Combine it all together and we get NN dimethyl butamide or NN dimethyl butyramide, right? Butyramide. So let's do some examples here. Some quick and easy stuff. Here's a simple one here. We have an amide over here, and we have a methyl group over here, right? Sorry, not a methyl, ethyl. There's two carbons. So that is easy as pie. That's ethanamide. Or, remember this is the beginning part of acetic acid, so it could be called, acetamide. I prefer acetamide because a lot of people call it that, and that's how you see it in bottles and stuff like that when you buy it. All right, next one. We have here 3 carbons, right? So that's a propamide. And then we have an ethyl group attached to the nitrogen, right? So that's an N-ethyl propanamide. Yeah, some of these are hard to say. Really hard to say. So there's a reaction, of course, that you can do with amides, just like you can do with amines. And that is the hydrolysis of amines. If I can get to that slide. There we go. Hydrolysis, remember, water, lysis, right? Breaking apart amines with water. It can undergo acid hydrolysis or base hydrolysis. And what it produces is the carboxylic acid and ammonium salt. Right? And the ammonium salt. There we go. Okay. So, here we have the amide here. Acetamide or ethamide. Right? And we have the acetate part or the ethanoic part, right? We'll combine it with some water and some acid and some heat, and our acetate regains its OH to become the acetic acid or the ethanoic acid, right? From there, right? And then this H right here goes over to rejoin the amine, right? Rejoins the amine. Along with a H from the acid, giving it a positive charge, making it ammonia. And then you left over the chloride ion, and so that's why you have ammonium chloride. Alright, ammonium chloride. So that's the acid hydrolysis. Base, very similar to, this time we have N-methyl propamide. Right, so here's the propyl part, and then the N-methyl part is there. Okay, N-methyl part's there. We'll add some hydroxide, sodium hydroxide, some heat. Right, and we already know what's going to happen, right? We already know that the propamide part will regain its oxygen from the hydroxide, right? We'll have a sodium ion left over to balance out that negative charge on the oxygen, right? And the leftover hydrogen goes to the amide part, giving you methamide or methylamine, right? So the difference here is that in an acid hydrolysis, we end up with the acid, the carboxylic acid, right, and an ammonium salt, right? Whereas it's reversed when you do a base hydrolysis, because here we end up with the carboxylic acid salt and an amine, right? So let's do a quick example. It says draw the condensed structural formulas for the products of the hydrolysis of N-methylpentamide with sodium hydroxide. Well, that right there tells you right now, since you're using sodium hydroxide, it's a base hydrolysis, which means you should end up with a carboxylic acid salt and a amine, right? Not a carboxylic acid and an ammonium salt. So the first step in getting this right, is to pay attention to what the name is. N-methyl, so there's a methyl on a nitrogen. Pentamide, 5 carbons, right? Easy. CH3, CH2, CH2, CH2. How many is that so far? 4. Time for the carbonyl, makes 5 carbons, right? And then the amide part, right? And then there was a methyl group attached to it. How did I know there was a methyl group attached to the amide part? Because of the N-methyl part right here, right? The N-methyl part. I'm going to add some sodium hydroxide, right? And some heat. They write out heat a lot in the textbook, right? But I like to use a triangle for heat. I think that's the first time I've ever told you that. But that's okay. Not a big deal. So then what do we end up with? Well, we're going to end up with the carboxylate version of this part right here, right? As a salt. So CH3, CH2, 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 COO minus, right? With a sodium ion, right? Along with the amine that we used, which was methylamine. Wow, my methyl really got messed up there. CH3. There we go. Right? And that's our products. It's as easy as that. So, our products are sodium pentanoate. Sodium. Uh-oh. It's giving out on me. There we go. Whoa, that's not how you spell sodium. Let's write that again. Surely you can tell that's a sodium. Here we go. Sodium. No. 8, right, is one product. And the other product is methyl amine. I'm sorry it feels like I'm pausing a lot when I'm like writing these things out, but I'm trying to get my pencil, my Apple Pencil, which is authentic. It's a real Apple Pencil. It shouldn't be giving me this much problems. But I'm waiting here for it to catch up to my writing. There we go. Methylamine. And then last but not least, I always say this, I would be remiss in my duties as a allied health emphasis instructor, lecturer, professor, right, if I didn't mention amides and their importance in health, in medicine. So, I don't know why I just drew up there. That's okay. That little guy, right there. Don't worry about that little guy. Okay, so amides in health, right? The first one is urea. Turns out that during protein metabolism, right, you produce some urea, which is this molecule right here, and it usually is removed by the kidneys and excreted in your urine, right? But the problem is that if you have malfunction in kidneys, the urea is not removed, it builds up into a toxic level, and that's a condition called uremia. Things you don't know, right? I just learned that myself. No, I'm kidding. Anyway, more interestingly though, there's these things called barbiturates, right? They're actually drugs that people take like recreationally, I think. I'm not sure. Anyway, these are cyclic amides, right? Of barbituric acid. Yeah, there we go. And they act as sedatives, and in small doses, and they're sleep inducers in large doses. Right? They're very habit forming, and a very famous barbiturate is phenobarbital, also known as luminol. Another one is pentobarbital, neem-butal, and these are right here. Right? Here's phenobarbital and pentobarbital. You'll notice that the only difference between phenobarbital and pentobarbital is what? It's in the name too, by the way. If you didn't notice, it's also in the name. Pheno, which comes from phenyl group, right? Is this guy right here. And guess what? On pentobarbital, that pheno or phenyl group isn't there. What's there? It's a 5-carbon alkyl group. That's why it's pentobarbital. And that's the only difference between phenobarbital and pentobarbital, which I discussed this with you a little while back, where drug companies and organic syntheses and organic chemists will go through and trying to achieve similar or better results from a drug will make minor changes to the drug molecule, retaining its main structure, which in this case is the barbital part, this part right here, right? And only changing the constituent part, which is where that phenol part is there, hoping to get a better drug or a more efficient drug, right? Because the most active form of the drug, at its very basic, is the barbital part, right? And then changing this constituent might have either adverse effects or have desirable effects as far as drug efficacy goes, right? I should have gone into drug development. I did a little bit of that, but it's I don't know. Who knows? We talked about this earlier, aspirin, right? But there's some aspirin substitutes that are made of amides, right? Aspirin actually didn't have any amides in it at all. Remember, it was salicylic acid, and then you added an acetate to it, so it became acetyl salicylic acid, right? Well, aspirin substitutes like Tylenol, also known as acetaminophen, right? There's this guy right here, and here's the acetyl part, which is the acetyl group, right? That's Tylenol right there. And another one is Phenacetine. I've actually never heard of phenacetine before, but that's phenacetine, right there. So, of these, for example, aspirin substitutes, what do you think is the main structure that's the most important here? And what's the substituent structure that gets changed by the drug chemist? I mean, not the drug chemist, but the organic chemist or the drug developer, right? To see if it can get a better effect. Well, the part that's important is it could be actually from here to here, all right? Because like that. And then the only thing changing is the R group that's connected to the oxygen, right? Which is also known as an ester, right? Or it could just be the entire. It could just be. It could just cut off right here, right? It's one of the two. I'm not sure which one. But the important thing is that there's this benzene part right here, and the amide, the secondary amide part with the acetyl group. That's the active structure, the what we call the business end of the drug molecule, right? Well, I think that actually ends today's lecture. I don't know how long it was. I didn't mean for it to be that long, but by the end of the day today, you should have turned in assignments 10 and 11 and quizzes 8 and 9 from last week, right? And by the end of the day, when you have them turned in, I'll post the answers for those assignments on Blackboard so you can use them to study for the exam. The stuff we went over today obviously will not be on the exam because you haven't got any of those assignments back yet. So here's assignment 12. That will be due next week, April 6th, along with quizzes 10 and 11 on April 6th too by the end of the day. All right, I'm going to say it again. Don't forget to study for your test. Thanks for hanging in there with me. I'll see you next time.